Okay, so how to generate formulas for nth order directional derivatives? And basically, we will do the second order like directional derivatives, and then later on we'll also go to the nth order directional derivatives, and we'll try to see how we can generalize the formulas. Okay, so first of all, you might have known that, let's say if I want to find how a function changes while moving in the direction of this vector cos theta comma sine theta, right? Um, we know about how the function changes in x direction, right? F sub x, which is basically the same thing, partial change of f with respect to the change in x. And similarly, we know how function changes in y direction, right? So yeah, using this, since we know that we are moving cos theta units in x, sin theta units in y, we will be able to find how a function changes while moving in the v direction, right? So yeah, we can just multiply cos theta with the partial f partial x plus sin theta with partial f partial y, right? So this is how the first formula is. It's pretty obvious. Now the main goal of this video is to prove the last two formulas. Okay, so let's see how we can get the formula. Now the second formula is basically about, like, if you want to again differentiate this function with respect to the vector v, like what if we want to again take the directional derivative of f with respect to b. So how will we find this? And this is in the notation we write it as dv square f. We are taking the double directional derivative, right? So yeah, let's go with the same definition. We have like defined the directional derivative of f with respect to b as cos theta times f sub x plus sin theta times f sub y, right? So let's use the same thing, cos theta, and don't forget that this is just the derivative of the function with respect to x, right? Now for now this is our function. So what I will do is I will try to take the partial derivative of this function with respect to x plus sin theta times the partial derivative of this function with respect to y. And yeah, this will make our life easier. Now we just need to make some manipulations and it will be proved. So now this is just cos theta times partial by partial x of, we know that this is cos theta the f sub x plus sin theta f sub y, right? Do understand that this is actually just the partial derivative plus sin theta times partial y by, this is again cos theta f sub x plus sin theta f sub y, right? Okay, now this is cos theta times cos theta. Now this is just partial square f by partial x square, right? Plus, now this is cos theta sin theta. And this is partial square f by partial y partial x, because it's already differentiated with respect to y, now with respect to x. Plus, this is sin theta cos theta times partial square f by partial x partial y. Plus, that's the sin square theta by partial square f by partial y squared. There are two partial y's. Okay, now from the Clairaut's theorem, we know that like the partial derivative of function with respect to xy, this is same as partial derivative of function with respect to yx, right? And yeah, and not just for two variables. Even if let's say I want to take partial derivative as a b c d, this is same as b c a d. Like anyway, like if the variables and the counts of the variables are same in subscript, like the partial derivative will be same. This is Clairaut's theorem, and we will be using this. Now from the Clairaut's theorem, we know that these two will actually just be same. So yeah, now I can say that this is cos square theta partial square f by partial x square plus 2 sin theta cos theta partial square f by partial x, or I can write partial x partial y as well, plus sin square theta times partial square f by partial y square. You might have noticed that this somehow resembles the cos theta plus sin theta whole square, right? And if you have noticed that, you are not wrong. Like later on we will see like how that's actually helpful to generalize this for the nth order directional derivatives. Yeah, but for now, yeah, let's keep that observation in place and go ahead to find the more formulas. So now we want to find the partial derivative with respect to u of the, we want to find the directional derivative with respect to u of the directional derivative with respect to b of f. So yeah, now our b vector was defined as cos theta sin theta, right? So we are dealing with it. Now let's define our unit vector as, and notice that we are dealing with unit vectors. Usually we take directional derivative with respect to unit vectors, right? Now this is cos phi comma sin phi, let's say. Now we want to find partial derivative, the directional derivative, with respect to u vector of the directional derivative with respect to b vector of the f, right? So we know that with this with respect to b, and let me just write it for first of all the simpler versions. The directional derivative with respect to b of f is just cos theta fx plus sin theta fy, right? So directional derivative with respect to u of f is just cos phi fx plus sin phi fy. Okay, now let's do this. So we know that with respect to b, it's just cos theta f sub x plus sin theta f sub y. Now again, now for this one, this will just be cos, now you use this definition, right? So cos phi and then partial with respect to x of this, our input cos theta fx plus sin theta fy, and again plus now sin phi and then partial by partial y of again the same, our input cos theta fx plus sin theta fy. Now I can write this as cos phi cos theta, and then this is just partial square f by partial x square, right? And this is cos phi sin theta, and now this is partial square f by partial y partial x, right? And this is sin phi cos theta times partial square f by this is partial x partial y, plus this is sin phi sin theta times this is partial square f by partial y square, right? So this is definitely a formula, but there's a really neater way of manipulating this formula. Now let me tell you something. Now we know that, like, the, let's say the part fourth derivative of f with respect to a b c, let's say third, it's just equal to the third derivative of f with respect to b c a. Note that this, the fact that the order does not matter, like leads us to define some new ideas, or like new notations, or the new way to deal with partials, because now I can just treat them as, let's say, partial c, partial b, partial a. Let's say it's the product of partials and then f over here. Okay, I can also write this as the partial a, partial c, partial b. Let's introduce this notation. Like this doesn't really exist till now, but yeah, I mean there does, but not in our world. I mean not in this video, right? So yeah, so if we, like, let's say that, like, we can write partials as product, and because they are product, their order doesn't matter, right? So yeah, that also helps us to write it as product. And whenever a partial meets a function, like the partial a times f is just partial f by partial a, right? So let us define in this way. So let us define this notation, and this notation works, right? Because the partials, in the partial, the order doesn't matter from the Clairaut's notation, the Clairaut's formula, right? So I can just write this as a product in this way. And whenever a partial meets a function, that's the same as the partial derivative of function with respect to that variable, right? So this notation will be helpful for us to generalize in few new things. So over here, now I can write this as cos phi cos theta. Let's say this is now partial x partial s f, right? And yeah, so whenever this partial x multiplies with f, that's just partial f with partial x. So there are two partial x. When they multiply, I get the same thing, right? Now I can write this as cos phi sin theta. I can write this as partial x partial y times just f plus, now this is sin phi cos theta. I can write this as, sorry, I can write this as this partial x operator. We can also see this as operators, just like when there's a number 3, let's say when multiplies with a 2, so this multiplies, right? I don't know what I don't know what I'm saying. Okay, anyways, you are getting the idea, right? So now this is partial x partial f plus sine phi sine theta partial I partial y f. Okay, so now we will deal them as product, right? There's a product between partial x. This is just product. This is normal product, right? Okay. Now let's see how we can make use of this notation. First of all, we can take f common from every term, right? I can just take f common, right? And now what I can do is I can just take from here. I can take in the first expression. I can take cos phi partial x common, right? If I do that, I just get cos theta partial x plus sine theta partial y, right? Again, from the second expression, if I take sine phi partial x common, I just get cos theta, sorry, sine phi partial y common. You cannot take partial x common. If I take sine phi partial y common, I get cos theta partial x plus sine theta partial y, right? And there's this f, like multiplying all of them, right? Okay, now again from here, if I just take cos theta partial x plus sine theta partial y common, if I just take that as common, cos theta partial x plus sine theta partial y, right? And again, well, again, the remaining thing will be cos phi partial x plus sine phi partial y, and there's this f that's multiplying all of them, right? Okay, now if I write in this notation, now notice that there's this new formula, obviously, but more than this formula, again, these are familiar to us. The reason how they are familiar is, now if we have that notation, now I can write this the directional derivative of f with respect to b, as I can write this as cos theta partial x plus sine theta just partial y operator times f, right? Similarly, I can just, and now from here, if I just remove both the f, so I can just define both the operator in terms of other operators. So I can define the directional derivative operator in terms of partial x partial y, and again similarly I can define this other operator in a similar way, cos phi partial x plus sine phi partial y. So notice that these two are just du and db operators. The thing that we have got over here, this is just partial b operator times this is just partial u operator times f, right? So now the fun thing is this: if we are taking one operator again, then other operator, these directional derivative operators are also can be written as the product, just like this, like partial derivative operators, like these things could be just written as product, right? We could just write them as the product. In this manner, we have seen that these directional derivatives can also be just written as products, right? So now the benefit of this is, now we have done a lot of steps to find the formula for the second order partial derivatives, right? We have to do a lot of things, but for now, let's say if I want to find, let's say if I introduce another vector, like u vector is just cos theta sine theta, right? Our b vector was, okay, I think our b vector was cos theta sine theta, I'm sorry. Okay, let's say this is our b vector, and let's say this is now u vector is just cos phi sine phi. Now let's see if our w vector is just cos alpha sine alpha. Now the benefit of knowing this fact is, let's say if you want to find first of all directional derivative with respect to w, and then directional derivative with respect to u, and then directional derivative with respect to b. If I want to find that, we know that this is just product, and that's really helpful. Now this one, and then this one, and then this one, and then f, and now we easily get the formula. Now I can just write this as cos alpha partial x plus sine alpha partial y, right? Because that is what this W is, right? We already found that over here. Like du was just cos phi partial x plus sine phi. Sorry, this is not theta. This is phi. I'm sorry. This is phi. I'm sorry for doing all of these small mistakes. Sine phi partial. Okay. Now the benefit is, now I can just write it as cos alpha partial x plus sine alpha partial y. Again, this as cos theta partial x plus sine theta. Oh, guys, this is not really partial x. This is partial sub x. These are operators. Man, I think this just ruins the video here. Okay, and sine theta partial sub y, and okay, and then sine theta partial sub y, and then cos phi partial sub x plus sine phi partial sub y, and then just f, right? Now you can just multiply these terms out to find, if you want to find this sort of rigorous formula, I mean this sort of formula over here, you can just multiply that out using our like idea of how, let's say if you want to multiply partial x partial y with f, we know that this is just partial cube f by partial y partial x, right? Now knowing this fact, you can just multiply this out and get the formula, but there's no need. We already know that how this is gonna be, and this is the answer, right? So this is how we can generate. And also now I think this should make sense now. This formula should make sense now, because we have, this is just partial b f, and we know that I can write it as just the product, right? So this will just be cos theta f sub x, not f sub x, partial sub x, cos theta partial sub x plus sine theta partial sub y, again product, again multiplied with the same thing, right? So that's the same as square times f. And so this was the reason, this is just partial square sub x plus, and if I multiply this with f, like this will be the result, right? I guess you know that. And this is just 2 cos theta sine theta, and this is just partial sub x partial sub y plus sine square theta partial sub y square with f, right? And now if I multiply f with partial x, again with partial sub x, sorry, so this will just be partial square f by partial x square. And yeah, this is how that formula makes sense now. So yes, so this is what I wanted to share with you guys. I don't know like how interesting this video was. I get stuck a lot in the middle. I'm sorry for that, but hopefully this made a bit of sense. This was a bit helpful, I hope so. So that's it guys, and I look forward to seeing you in the upcoming videos too.